There was one problem on the lesson last class that we didn't quite get to, and I just want to make sure that you're comfortable solving these differential equations, particularly when they involve u-substitution. Just like the other examples that we went over in class, this one's asking us to find the solution to a differential equation given a function value on the solution. Now, let's try to visualize what exactly we're trying to find. That differential equation is going to have infinitely many solutions. And what you're looking at here is something we really haven't talked about yet. It's called a slope field. Now, I don't want to go into too much detail on slope fields here because we haven't really talked about them. But again, we're just trying to visualize all the different possible solutions to this equation. Now, the solution that we're interested in must pass through this point 0, 1. And we'll find exactly what that function is. But just to give you a little preview of what the graph looks like, let's take a look here. It's going to look like a kind of a sinusoidal kind of periodic function and then shoot up exponentially. So now let's talk about how we're going to find that solution algebraically. First, we want to separate the variables. We want to move all the x's to one side and all the y's to the other. This is called separating the variables. And we can do that pretty simply here by just multiplying both sides by dx. There's a little bit of hand waving there with multiplying by dx, but we're going to let it slide for now. Next, you want to integrate both sides. The integral of the left-hand side would just be y plus c, and we'll deal with that constant in a minute. But the integral on the right-hand side is going to be a little bit more involved. We're going to split this up into two separate integrals and use a u-substitution on each one. For this first one, we can let u be 4x, which would mean that du is 4dx. Now, we don't have a 4dx to substitute in this expression, so we'll have to manipulate that a little bit and get 1/4 du equals dx. So that now we can replace the 4x with u and replace the dx with 1/4 du. Now it's time to actually find the antiderivatives. The antiderivatives of sine u should be one that you have memorized, and it's negative cosine u. So when we integrate this sine u du, we should get negative 1/4 cosine u plus c. And since we said that u was 4x, we can replace that u with 4x and be done with this part of the integration. Now, let's take a look at the other one. We have the integral of e to the 3x dx. In this case, we want u to be 3x, which would mean du is 3dx. And just like with the last one, we don't have a 3dx to substitute, so we'll have to manipulate that equation into 1/3 du equals dx, and now we can make our substitutions. We can change the 3x to u and change the dx to 1/3 du. E to the u is going to be another one of those antiderivatives that you should have memorized. The antiderivatives of e to the u would just be e to the u plus, again, some other constant. Now, looking at this equation, we see a bunch of c's in the mix here. We have three different instances of a constant, and they're all different constants, and we haven't distinguished them in any way, and that's okay. We're going to combine them all into one. So what we want to do is combine all of these constants into just one constant. We can subtract that c over on the left-hand side with the y, and combine the two constants on the right-hand side with that to just come up with some other constant. A constant plus another constant minus another constant is just going to be some other constant, so we're going to leave just 1 plus c on the right-hand side. This equation with the plus c is actually all of the antiderivatives that would have that dy dx as its slope equation. But we are looking for a specific one. We want this equation to pass through the point 0, 1. So we need to find the c value that will allow that to happen. Now, this is pretty easy. All you need to do is substitute 0 into x and 1 into y, do a little bit of arithmetic and algebra to isolate the c, and we can find the c value without hopefully too much trouble, and it is 11/12. Now that we have the c value, let's plug it back into the c that we had in our solution equation. So instead of having all the antiderivatives, we just have the one antiderivative, sometimes called the particular solution to the differential equation. This is going to be our final answer, but let's go back and try to understand what we just found in context. The solution to dy dx equals sine of 4x plus e to the 3x, given that f of 0 is 1, would be y equals negative 1/4 cosine of 4x plus 1/3 e to the 3x, plus 11/12. So let's look at that slope field again that basically just maps out all the antiderivatives. We'll plot the point that we need to go through one more time and take another look at the graph. You don't need to know how to graph this or anything. I think it's just kind of cool to see it in action. Thanks for watching. Y'all have a great day.